They seemingly appear out of nowhere. They glow, sometimes they split, and then they vanish without a trace. Scientists call them plasmoids, others may call them orbs. But whether they appear in the lab, on camera, or in the sky, these structures are real. And in some cases, they appear where we least expect them in the Earth's atmosphere, on radar, and even in one's own backyard. In physics, a plasmoid is a real structure. It's not a theory, it's not a metaphor. It's made of plasma, the fourth state of matter, that ionized gas shaped by electric and magnetic fields. And under the right conditions, it has the ability to organize into something stable, sometimes eerily stable. So in this video, we are going to look at how plasmoids form, what they are, how they move, where they show up, and what they might help explain. We'll explore the physics, the fields, and the energy that makes them possible. Then we will look at why people connect them to high strangeness and where the science stops for now. Because if we're being honest, the line between the explainable and the mysterious is not always crystal clear. And recognizing that without pretending otherwise is an important part of science. Don't worry, you'll know which parts are backed by research and which are pure possibility. And if you're into science that doesn't stop where things get strange, this one's for you. To begin, a plasmoid is a self-organizing structure made of plasma, a cloud of charged particles that holds itself together through a balance of forces. At first glance, it looks like a glowing ball or a spinning loop, but inside, it's alive with motion, currents flowing, fields bending, particles spiraling in and out of alignment. What makes a plasmoid different from ordinary plasma is that it is confined by its own electromagnetic structure. As charged particles move, they generate magnetic fields, and those fields in turn guide the motion of the particles, creating a feedback loop that can trap plasma inside itself. It's like a whirlpool made of fire, motion creating structure and structure reinforcing the motion. The result is a kind of natural containment, a region where inward forces meet outward motion, reaching a temporary balance. This interplay is described by magnetohydrodynamics, or MHD, the study of how charged fluids behave under the influence of electric and magnetic fields. The most common shapes we see are toroidal, like smoke rings made of plasma, but depending on the field geometry, plasmoids can also form spheres, columns, or filaments. What holds them together is not a physical shell. It's a pattern, an arrangement of motion and energy that becomes stable, at least for a while. Once you recognize the pattern, plasmoids start showing up in surprising places. You can find them in fusion reactors, in Earth's magnetosphere, in solar eruptions, and possibly on your next camping trip. So wherever energy flows and fields collide, plasmoids can emerge, brief structures born from chaos. So now let's take a look at how these structures actually form. To understand that, we have to start with something invisible, magnetic fields. Magnetic fields are found wherever electric currents flow, and in plasma, currents are everywhere. You see, plasma is made of freely moving electrons and positive ions, and that's what makes it so electrically active. And that's ultimately why space is not empty. It's full of charged particles since space is made of 99% plasma. We have charged particles moving, colliding, creating vast, tangled magnetic landscapes. In some places, magnetic fields run in opposite directions and get pressed closely together. These narrow boundaries are called current sheets, regions where energy builds under tension. At first, everything holds. The magnetic lines are stretched tight, just like elastic bands in a net. But over time, the stress becomes too great. And that's when magnetic reconnection begins. Magnetic field lines are not physical things. They're visual tools that help show where magnetic forces go. But when reconnection happens, those forces reshape. The field line snaps into a simpler configuration, and the stored energy is released into the plasma. Now, that energy does not vanish, it gets transferred directly into motion. Plasma near the reconnection zone is pulled inward, then flung outward fast, and in some cases, it coils into a loop. The magnetic field closes in on itself, trapping plasma inside. Sometimes a plasmoid will detach and drift away. Other times it pulses, merges, or splits. We'll come back to those behaviors later, but the core pattern is this: a buildup of tension and a sudden reordering of the fields that hold everything in place. Wherever you have plasma, magnetic fields, and stress, you have the ingredients for a plasmoid. This is where they begin. This is where they are born. Now that we know how plasmoids form, the next question is, where do they show up? Plasmoids are not rare. They're just rarely recognized. There's a difference. Once you know what to look for, you start seeing the pattern repeat. All it takes is those three ingredients we talked about: charged plasma, magnetic tension, and a sudden release of energy. Let's start big in terms of where to find them and work our way home. Starting out in interstellar space, plasmoids may quietly shape stars and galaxies. They have been observed in solar wind where magnetic fields fold and reconnect. They likely form at the edges of astrophysical jets. The plasma streams launch from black holes and neutron stars. Here, plasmoids can be enormous, forming slowly, lasting longer, but built on those same rules: reconnection, closure, and magnetic balance. Then we have the sun, our natural plasmoid machine. Its magnetic fields constantly twist, fold, and erupt. During solar flares and coronal mass ejections, field lines reconnect and Earth-sized plasmoids launch into space. We've seen them in coronagraph images, loop structures wrapped in magnetic fields, drifting through the solar wind. Some last for hours, some collapse in seconds, but the physics in all cases is the same. Now let's move closer to Earth, where Earth's magnetic field forms a long tail behind the planet, a region where the plasmoids form quite regularly. When stretched, magnetic field lines snap back into place and plasmoids shoot away from Earth, a process we have confirmed with satellites over and over. Even closer in, short-lived plasmoids can emerge during auroras and ionospheric storms, appearing for just a moment and then poof, vanishing again. Here on the surface of Earth, they sometimes show up. We have ball lightning, earthquake lights, and volcanic glows. These may all be atmospheric plasmoids, glowing spheres that appear during intense electrical activity. They have been reported near fault zones, volcanoes, and storm clouds. They've shown up on radar, they've been captured on video, and in a few rare cases, they have been recreated in the lab. Wherever energy builds and magnetic fields twist, plasmoids can appear. Whether it's a black hole or a thunderstorm, we find the story repeating. And when plasma organizes, it can glow, move, or vanish. Which leads us to our next question. Well, what makes them stay and what makes them disappear? Now, plasmoids don't just drift through space like clouds, they hold together. And that stability is not random. It's the result of balance. Inside a plasmoid, charged particles spiral along magnetic field lines, creating electrical currents. Those currents generate magnetic fields, and those fields push inward, trying to compress the structure. At the same time, the plasma pushes outward, driven by heat, collision, and particle motion. This dynamic, inward compression versus outward pressure, defines a stable plasmoid. It's a feedback loop. Here we have movement that shapes the field and the field shaping it back. But that balance is delicate. If the magnetic field weakens, if charge leaks out, or if something disrupts the environment, the feedback breaks. Without containment, the particles scatter, the shape dissolves. What was once coherent becomes ordinary again. To an outside observer, it would look like the plasmoid simply vanished. But what disappears isn't just the shape, it's the pattern that held it together. Like we said earlier, some plasmoids last only for milliseconds. Others persist for minutes, even hours, especially if they are fed by outside currents or nested inside a larger magnetic field. But none of them are truly permanent. Every plasmoid is a fleeting arrangement, a moment of order held in place by balance. And when that balance breaks, the structure collapses. But sometimes before that collapse, they do something even stranger. They split, they merge, they orbit each other like they're alive. And that's where we're going next. Plasmoids don't just form, they move, and sometimes their movement looks deliberate. In labs and space, we've seen them merge into larger structures, split apart, or even orbit each other like tiny dancers in a magnetic field. But none of this is random. When two plasmoids with compatible magnetic fields come close, their fields can reconnect, snapping into a new configuration that lowers the system's energy. The two structures merge into one larger, more stable plasmoid. Now, when a plasmoid becomes unstable, like if internal currents get too strong or if the field symmetry breaks, the structure cannot hold itself together anymore. The containment ruptures and smaller plasmoids pinch off from the original. That's what we call splitting. And then there is the motion. Plasmoids can spiral, chase, or circle each other, not because they're alive in the biological sense, but because they are responding to electromagnetic forces. They attract, they repel based on their current and field orientation. Now, these movements may look intentional, but they are complex feedback between charge motion and magnetic structure. In the lab, we have watched these patterns unfold, orbiting loops, linking filaments, movement without contact. What we're seeing is physics in motion, emergent behavior from simple rules. Still, when you see them move, it's hard not to wonder, is something more happening here? Now, we've looked at plasmoids in labs, in space, and in the sky, but some sightings do not fit into these categories. For centuries, people have reported glowing orbs that float, pulse, or vanish without a sound. Some drift across battlefields, others appear indoors, some flash across remote hillsides, and all of them tend to leave no trace. We don't know if all of these are plasmoids, but the shapes, the motion, the strange consistency, it's worth paying attention to. Here are two examples you're likely very familiar with. In 1561, over the city of Nuremberg, dozens of spheres crossed the sky. In 1977, in Petrozavodsk, a glowing object changed shape over an entire city. Many of these may have natural explanations, but some not yet, and I don't claim to have the answers. But if you've ever seen anything like this, a strange light, a silent orb, share it in the comments. We all want to know more. Now, I understand that stories are not necessarily proof, but patterns are important. And I think if plasma can do all these amazing things out in space, why wouldn't they be able to do it closer to home? Plasmoids remind us that even in chaos, structure can arise. That tension does not always tear things apart. Sometimes it holds them together. So whether it's a burst of plasma in a fusion lab, a filament in space, or a quiet light drifting across your backyard, what matters is that it makes us look closer and maybe wonder what else is out there, holding itself together. Thank you so much for joining me today. I cannot wait to hear what you have to say. And until next time, take care.